my name is Jun Nakajima from Intel, and then we do this, together with Tianyu, and I'll cover the first part, essentially the introduction about Xeon Phi, and then followed by, his talk. Okay. So this is it's kind of in a way some experiment project, but because I need some disclaimer at this point, because BT is not enabled by default on Phi. So if you guys are interested in, you guys should talk to us. Okay, so this is kind of disclaimer. So I started with the introduction of Xeon Phi, what it is, and then how it's used in the cloud, okay, and bunch of optimization we needed to get high performance. By high performance, I mean basically near native performance, like more than 95 performance over the native system, HPC system. Typically, HPC guys don't use virtualization. That's the reason by default VT is not enabled. But in this project, we actually use the VT, okay? So if you look at the internet today, we have a lot of data, right? And on the cloud, we need to analyze those using, for example, machine learning or deep learning or AI, and then to process those, a lot of data, we need parallel processing, right? And as you see, this is our kind of product. The Phi is a bit, it's outstanding in terms of cores and then threads. So let's take a look at. Before that, to have a high performance computing, those are the key factors, like cores, number of threads per core, and vector width, and then peak memory bandwidth, right? So if you look at number of cores, compared with the Xeon, Haswell, the Knights, Knights and the Knights Landing has much more cores. Then also, if you look at threads per core, it's basically 4. So then, if you look at number of logical processor, it has a lot, actually 288 on Knights Landing. And also the vector width. This is required for vectoring, instructions. Yeah. I just pause a little bit because people coming in. And then, vectoring, vector width is important for vectoring instruction because I don't know you guys are familiar with the vector, instructions, but basically those instructions take a look at multiple data elements, right? Like 4 or something like that. Then calculate simultaneously, and then put the results simultaneously. So with a single instruction, you can calculate like a 4, instruction kind of thing. Okay. So that's the important for parallel processing. Okay. And the memory bandwidth is also important, right? Because on the HPC, you have a huge data. So it's unlikely you hit the, cache, right? So that's the key. So those are, again, the key elements of parallel computing, high performance computing, okay? Then, as you see, if you compare those, the Xeon Phi is a Knight, right? Are actually it's outstanding, okay? And this processor is also interesting. This is the one we just introduced, okay? It's not introduced, it's now a product. And one notable thing is it's self-bootable, okay? it used to be work as just a coprocessor. The coprocessor means like a graphics card you put into the PCI slot, okay? Then in terms of computing, it's kind of a separate entity. You need to copy the data sets to the coprocessor, and once that computation is done, you get back the results. However, in this case, the Xeon Phi itself can run operating system. You don't need to do that, and you can run application in that operating system. And actually, we are able to run various operating systems, including Linux, Zen, and then Windows, for example. Okay, so that's one notable thing. And then that really means it's binary compatible with Xeon. Okay, and the other thing is, in the previous page, I talked about memory bandwidth. This machine has a high bandwidth memory, sometimes called HBM, okay? And also it has the very fast interconnect called Omni-Path. That's required for, I don't know you guys know about MPI. That's typical inter-node communication for HPC computing, right? So that's also there, okay? This is just, where it's the kind of history. We had the Knight's Corner. Again, this was just a coprocessor. Now this is a self-boot. And then we have a newer version, generation as Knights is also coming soon. Okay, now I have more details on Xeon Phi, Knight's Landing, okay. It's kind of amazing, and for example, we have 36 tiles and then tiles are there. So on each tile, we have 2 cores, okay? You can see 2 cores, right? And on each core, we can have 4 threads, okay? And then each thread has each core has 2 vector processing unit. That is used for, ABX 512, that kind of thing, okay? And then I mentioned that high bandwidth memory, that is MCDRAM, okay? So from a hardware point of view, this is amazing, but from software point of view, this is a challenge, right? Because again, the number of logical processor is 288. And that's challenging even a native system, right? Now, if you run this in virtualization, that's even more challenging. So we're going to talk about what kind of challenges we saw and how we solve. Okay, so I'll switch to Tianyu.
I will continue the topics. MCDRAM unpackaged memories provide 3 kinds of memory modes. The first is cache mode. This mode, the MCDRAM will work as the memory side cache between the CPU and the DDR. This mode is totally software transparent. Software doesn't need to be optimized and can get benefit from the cache. The second mode is flat mode. In this mode, all the MCDRAM work as normal memories and in the same physical address space of DDRs. Software needs to be optimized, allocated important data in MCDRAM to get better performance. The third mode is hybrid mode. In this mode, some part of MCDRAM work as cache and the other part work as normal memory. Motivation for this mode is to benefit all kinds of software, since not all software have been optimized for the flat mode. In our HPC cloud usage, we just use the flat mode. When MCDRAMs in the flat mode, Plan4 exposed 2 NUMA nodes. One NUMA node is for CPU and DDR memories. Another NUMA node is for MCDRAMs. To make sure non-important data out of MCDRAMs, the NUMA node of MCDRAM has a far distance to the NUMA node of the CPU. When system boot up, it will allocate the memory from the DDR memory by default. The software wants to use the MCDRAM, it needs to allocate the important data in the MCDRAM explicitly via some new kind of interface. Next, I will introduce our HPC cloud usage. We will just create a single VM on one machine and expose the most host CPU to the VM. Just we have mentioned, we have up to 288 logical CPUs. So we require the VM can support more than 255 vCPU in a single VM. We need to expose the MCDRAM to VM to let the HPC workload access such kind of high bandwidth memory to get better performance. The VM also needs to connect with some other computing node via the low latency and high throughput connection. So we need to pass through the Omni-Path fabric to the VM. To support such kind of huge VM, it brings some challenge for them. The first challenge is to support more than 255 vCPUs. Now HVM gets to just support 128 vCPUs. To support more than 255 vCPUs, it requires active APIC mode. Legacy X-APIC mode just supports 8-bit APIC ID. It limited the vCPU numbers. It just can support 255 vCPU at most. One APIC ID is reserved for the broadcast ID. Active APIC mode can support 32-bit APIC ID. Increases the supported CPU. But in the Linux kernels, it disables the active APIC mode when there is no IRQ mapping function. The reason for that is that the IRQ cannot be delivered to CPU which index is more than 255. So if we want to enable the more than 255 CPU, we need to enable the IRQ mapping function. It's one of the IOMMU feature. So it requires the virtual IOMMU support in the VM, but currently Xen doesn't have such kind of support. So the dependency chain will look like this. We need the active APIC IRQ mapping function and the virtual IOMMU. There is another driver dependencies. Linux IOMMU drivers cannot work without DMA translation. It will fail to probe if there is no DMA translation function. So we need to enable it first and then the IRQ mapping. We have a high-level design for the virtual IOMMU support. Next, I will go through it quickly. In our design, there are two parts. One part is the virtual IOMMU device model. It will in the Xen hypervisor. Another part is the damaged virtual IOMMU. It works as a hypercore wrapper in the QEMUs. When VM is created, it will create the damaged virtual IOMMU in the QEMU first. The damaged device will pass the input parameters and query virtual IOMMU capability that the hypervisor can support. If it meets the requirement, it will create the virtual IOMMU device in the hypervisor via hypercore. OS probes the IOMMU via ACPI DMAR tables. Now all the ACPI tables are built in the HVM loaders. So HVM loader needs such kind of information that whether virtual IOMMU is enabled or not, and what kind of capability it should support. So the damaged virtual IOMMU device needs to notify HVM loader with this information while then store interface. This part is for the creation. For the DMA translation, when VM enables the DMA translation, it provides the mapping table from IOVA to GPA and write it into the virtual IOMMU device model. For the virtual PCI device, it's in the QEMU. QEMU has already provided a virtual IOMMU framework to deal with the DMA translations. It provides a hook. The DMA device module will register a callback. When there is a DMA translation request, it will pass the request to the hypervisor. Virtual IOMMU will do the translation from the IOVA to the target GPA and then return back. Then the QEMU will access the target GPA. For the physical PCI device, the translation is done by the physical IOMMU and translates the IOVA to the HPA, while guest just provides the mapping table from the IOVA to GPA. So we need to create a shadow page in the virtual IOMMU device model. Translate the GPA to the HPA and update the shadow page table point to the physical IOMMU. Let's it to finish the DMA translation. Next part is for the accurate mapping functions. When VM enables the accurate mapping function, it will provide an accurate mapping table to the virtual IOMMU. The IOQ from the virtual PCI device and the physical device will finally deliver to the virtual IO epic and all the virtual MSI depends on the IOQ type. In the traditional way, this model will find the target virtual local epic and inject virtual interrupt. But in the IOQ mapping mode, it needs to consult with the virtual IOMMU to find the target virtual local epic and then inject the virtual interrupt. This is all our design for the virtual IOMMU. Next challenge for CN is scalability. We find a scalability issue when we test the performance in such huge VMs. Now the task work list are per CPU data structures, but in current code we use a global spin log to protect all this list. This will introduce a lot of overhead. When running heavy workload in the VM, because there are a lot of timer requests from the VM at that point, hypervisor inject back the timer interrupt via the event channel in the task list. At that point, the task global log will become a hot point. So we try to change the task list log to the per CPU log. The performance data increase a lot. We test the performance in the VM via three kinds of benchmark. Stream as a benchmark to test the memory bandwidth. We test MCDRAM bandwidth via this benchmark. And DG and SGM as for the float point computation capabilities. After this change, the string data is increased from 63% to 87%. And the DGN and the SGM data is increased from 15% to about 85% compared with the data on the host.
DGN is a matrix calculation data, right?
This is with Zen 47, right?
Yeah.
And these are one vCPU guests.
No, it's the oh, you one socket.
200.
Yeah, the VM has about 256 vCPU.
So this is one single VM.
Yeah, one single VM, right?
And all of them are doing timer, which is causing a contention on this.
Yeah, we yeah.
Okay.
No. Next chart we will introduce how to achieve high performance in such huge VM. First, we need to expose the key compute result to VN. The first is the CPU. How to expose the CPU to the VN? HPC software will assign workload according to the CPU topologies. Let's try to balance the workload among the physical cost to take advantage of the physical cost efficiently. So we need to keep the CPU topologies in VN as same as on the host. 4 threads per core, and pin the logical threads of the same physical core to one virtual core. We left some physical cores for the domain 0 and pin the CPU. This can help to reduce the overhead introduced by the context switch, since the VM and the domain 0 run on different kind of CPU group. The second one is the MCDRAMs. We need to expose the high bandwidth memory to the VM. We should create virtual NUMA nodes as the host NUMA topologies. One for the virtual CPU and the DDR memory. The other one is for the MCDRAMs. We need to keep the NUMA node of the MCDRAM has a far distance to the virtual NUMA node of the CPU. And then the HPC software can find the MCDRAM and use it in the VN.
This is just what mimicking what the native is doing. So.
Yeah. During test performance in the VN, we also find there are a lot of interrupts when running the benchmark or some heavy workloaders. And at the local epic timer interrupts cause a frequent VN exit. For example, running the string benchmark, we find it costs about 26,000 VM exits per second. So we hope to reduce the timer interrupt. We set the timer slop same parameters set it to the time milliseconds.
Is that test dependent, workload dependent, 26,000 exits per second?
Excuse me?
Was it while the test was running, was it because of the nature of the test that you have?
String.
Even idle, right? Even idle, we see this one, right?
No.
Idle is not there. When you run some application, we see this.
Yes, string benchmark.
Also stream.
But why would stream have set so many timer interrupts? Why are there so many?
As the request from the guest. So far, we are still in the investigation.
Yeah.
Sorry.
Just Linux kernel is just.
Yeah, we
Linux kernel wouldn't do that.
Then maybe the benchmark.
Yeah.
Yeah, the benchmark. So
You mentioned local APIC, but doesn't it have VAPIC? Or does Knights Landing not have VAPIC to bypass?
This one doesn't have it yet. No.
Okay, so the other question is, if you're doing guests with PV extension, you would be using the Zen PV calls for timers.
But the timer we need to virtualize, right?
Well, that's partially the timer in Linux uses the Zen PV framework. The single shot,
Oh.
that's what it uses. So that's why I'm trying to figure out where you get the APIC timer.
yeah, from my view, I have a basic idea.
It's an HVM guest, right? So
Yeah, but HVM
Yes.
gets PV.
Yeah, can you see that? The guest uses the CNPV timer and then it sets a request to the hypervisor.
What do you mean the hardware local APIC timer gets used?
Yeah,
Okay.
it uses the local APIC timer to implement the PV timer.
Right. Okay.
Okay, answer your question. And then when there are interrupt, it will cause the guest VM exit.
just something is still asking for is 26,000.
Yeah, that's, yeah, the hypervisor does it on behalf of it.
So on that node specifically, there is a patch series from Oracle to introduce a TSC time source. have you experimented with that code? So it would replace the use of the local big timer.
No, we
We're talking about Oracle code. There's also per CPU tasklet, like Oracle.
Yeah.
so we don't change the code, just set the timer slope parameters. It can help to increase the timer interrupt in interview, and then reduces the timer interrupt, local epic timer interrupt. After this change, we can get very close native data. The stream can reach about 99%. DGN and SGMs can go up to the 97%. So we can achieve the high performance, but that way has a side effect. We have a low timer's resolution. We still try to find some trade-off solution between the timer resolution and the performance status. We have some thoughts. First, from the hypervisor views, since we just run one single VM on one machine, so scheduler may be not necessary. Then that can help to reduce the schedule timer request. From the guest view, we can make the guest Linux kernel tick list to remove some periodical timer. We are still analyzing the timer request in the VM, in the guest when running some benchmark.
Yeah, so this is
yeah, also,
kernel.
yeah, we are still in the investigations. We hope to remove some redundant timers, but it's very hard to change the guest if we provide the cloud service. So this is next to do. Call for actions. We are able to achieve high performance HPC on Xen, but some changes are required in Xen. First is the increased vCPU numbers. This task can be divided into two parts. First is increase from the 128 to 255 vCPUs. This task doesn't require some new features. And the second is virtual IOMMU. We have posted a high-level design to the Xen mail list. We hope the community can give more input or comments to push the feature upstream as soon as possible. These two tasks can be done in parallel, since they don't have a dependency. Okay, this is all my topic. This is question and answer.
So while I agree that virtual IOMMU is a useful project to do in general, I'm trying to see the dependency chain brought you to requiring a virtual IOMMU for high performance, right? So you need it for higher CPU scalability, which needs the X2 APIC mode. So you can target more CPUs.
Yes.
Which needs interrupt remapping.
Yeah.
And then the interrupt remapping, because it's implemented in VTD or...
Yeah, it's an IOMMU feature.
So but can you para-virtualize any of those and break that dependency chain? So can you do interrupt remapping as virtual interrupt remapping without requiring...
Assuming you can change the Linux kernel, for example, right? You can remove some requirements.
Yeah, we have done such change. Yeah, we remove the dependency in the Linux guest. It's a very simple change. Just when check whether the IOQ remap function is available. If in current code, it will disable X2 APIC mode, but we remove the desk code, and we can boot up more than at most we can boot up 400 vCPU in a single VM. But this is hack ways. It cannot be accepted by the upstream.
What about, I mean, so HVM has the PVH, the PVHVM mode, that allows you to have the PV event channel interface rather than the X2 APIC stuff. Does that, if you use the Xen's existing PV interfaces, would that allow you to scale up without this limitation?
No, because that's into the Linux subsystem that decides that you've got more than 250 CPUs to use interrupt remapping. You still
Probably
get
generic
side
code.
dependency.
Sure. But in order to implement interrupt remapping, you should not have hard-coded assumptions in Linux requiring VTD or IOMMU.
Yeah, we have tried to.
But looks like Linux just needs to detect the interrupt remapping, right? It's not really using.
That's what we're using. Yes.
You need to use. But
Yeah,
you
when-
said you remove that check-in, but still it boots, it runs fine, right?
If the function is available at where use, because we have no such kind of hierarchy remapping function support, so at we are not use it.
Strictly speaking, the only thing you actually need interrupt remapping for is for IO8-bit entries, because the IO8-bit format strictly has an 8-bit ID in it. One of the things we're considering with PDH guests or HBM Lite or DM Lite 2 or whatever we eventually decide the name is going to be, is that in cases there you can get away without having a virtual IO8 in the guest. So if you're a plain VM that's got no devices whatsoever, or indeed a plain VM that has SRO we pass through only, in those cases you don't need an IO8 at all, and it's a smaller attack surface from the hypervisor point of view. You just don't provide one. Under those circumstances, it would be fine to have more than 255 vCPUs and running X2APIC and not needing any guest IOMMU. Of course, someone's got to persuade the Linux x86 maintainers that that's a sensible thing to do. Good luck to them.
But the virtual IOMMU is used for other things, right? You were talking about it.
Yes.
For other reasons anyway. So
Well,
it certainly won't hurt, but
There is actually already one virtual IOMMU implemented in the hypervisor, but it's very clear it's never actually had any testing because anytime you turn it on, stuff goes bang. AMD implemented a virtual IOMMU for their APU cores that are the same thing that are in PlayStation 4 and Xbox Ones. But the code has never ever been turned on because when you do turn it on, things go a bit wonky.
My concern is once we need virtual IOMMU or interrupt remapping in VM, then if Linux starts using, then you may generate yet another performance issues,
Yep.
right?
Yeah. Well, the virtual IOMMU will be just
Yep.
functionally complete
Right.
with no performance tuning yet. It's a long way to go to tune the virtual IOMMU. So.
Any question? Okay. Huh?
Sorry, one question. The MCDRAM,
Mm-hmm.
the way you presented it in the hardware view first, made it sound like that's higher performance than the DDR memory.
Right.
Yet when you expose it in virtual NUMA, you expose it with less proximity to the CPU than local memory. So it's in a different NUMA node.
No, it basically kind of cheating cheating just Linux, because if we show as just a DRAM or whatever, then Linux would use.
But isn't that what you want for performance?
Well, what we want is just make the memory available to application only, just to bypass whatever Linux. So don't touch the memory for kernel, for example, memory allocation.
I see.
Right, it's dedicated for application.
And the applications make use of the NUMA library
Right.
to request.
Okay. Yeah. That's currently like kind of hot. We're kind of working on spec, ACPI, should be in the ACPI.
so would you guys be interested in implementing a simple placement scheduler that just, you make a CPU pool and it goes bam, 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 it puts one vCPU on one PCPU and then doesn't do anything?
Yeah.
We just
So you guys gonna help with that?
so far we just ping the vCPU on the one physical CPU.
Sure. I think there's lots of use cases for.
Yeah, also Wei Dong mentioned, like, we're gonna their customers are asking for PA VMs,
Yeah.
right? And
Yeah.
one VM on a single system, for example.
Yeah.
Yeah.
Yeah. Well, I think there's lots of use cases, I think, for having a scheduler that does hardly anything.
Right.
Yeah.
Basically doesn't do anything. It just
Yeah.
you have vCPUs, it says bam, 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 bam.
Uh-huh.
And if you have more vCPUs than you have pCPUs, it says sorry.
Yeah.
What other performance testing have you done on VMs of this size?
Excuse me.
You say your VM is what, 255 CPUs?
Yeah, I run 256 vCPU.
Okay, so that was the streams benchmark.
Yeah.
What other performance tests have you run?
DGIM and SGIM.
Just those three.
Yeah, just the three.
And
So
those
far
are
we
the
just
key benchmark for HPC.
yeah, it's dedicated for the HPC.
If they are fast, then we can predict the,
What about the traditional, like, top 500 Linpack kind of HPC?
We also ran RIMPAC. Yeah.
Out of interest, whilst you're doing this, do you have a hypervisor with watchdogs enabled?
Excuse me.
Crazy people do that.
Yeah, only crazy people do that. No,
Do the watchdog timers? Do you know?
Yeah,
So at the
yeah,
moment,
I have.
at the moment with Zen, in any 64-bit HVM guest, I can crash the hypervisor.
64 vCPU?
64 vCPU, which is why Zen server is currently limited to 32 and isn't getting bigger anytime soon. Specifically because you end up waiting for more than 5 seconds synchronously in the hypervisor at some point.
Okay. Yeah, I have
typically-
a asked a question in the mail list. Yeah.
Quite a few times this is to do with...
But for our test, we don't find the crash. So maybe the test, the workload are different.
Well, specifically it's a crash because of the watchdog timeout. It's an artificial crash after detecting a bad situation.
Okay.
A number of the improvements that we did in the 4.7 time period, so things like per vCPU read-write locks, the change in the EPT flushing, and ticket locks. All of those were required to get our limit from 16 vCPUs up to 32 vCPUs. But I'm quite conscious that even at 64 vCPUs, a malicious guest can do very nasty things to the hypervisor.
Is that dependent on your hardware platform, how many cores you have? Because they have 228 physical cores.
Yes, but it's
You're not doing over.
You're not doing any
no,
visual.
don't need overcommitment. It's
Any
just,
NUMA memory effects?
it's not that spin locks being held for more than 5 seconds, things like that. The problem is the algorithmic complexity in the hypervisor for certain critical operations.
But if you have only single VM, right, you just pack hypervisor, you just kill yourself, right?
Right, yes.
I'm not sure the point of
Yeah, or with CPU pinning where you don't rely on.
That doesn't help you. CPU pinning doesn't affect how long you hold a spin lock in the hypervisor for.
So as long as your Linux is okay with suddenly having the world's freeze for seconds at a time, then you're okay.
And indeed, it's fine if you're doing some on-premises HPC where you say, well, I'm both the server administrator and the VM administrator. I trust myself not to shoot myself in the foot. Unfortunately, from Zen Server's point of view, we also have cloud customers that we need to care about, where anyone with a credit card can come along and try and do the nastiest things they can think about to your...
Or Bitcoin miners.
They tend to keep themselves to themselves, and they take up a lot of CPU time, but yeah, they're paying for it, and it's not economical to mine Bitcoin on CPU these days.
Related to that, Zen changes number of CPUs. Did you need to change anything for supporting 4 hyperthreads per core? Because there's at least in Linux, I think there's assumptions built in all over the place that a core can only have 2 hyperthreads.
There are always some assumptions like that in scheduler too. But yeah, I think as long as you're pinning the vCPUs, it doesn't matter.
Because he is pinning, and when he pins, he knows which threads are in which form. So that's basically avoiding any scheduling change.
When I put up about 200 pages, it's going to be I don't need some problem on scheduler. So I didn't dig more. But yeah, I found the issues when I run such a huge VM, when the RTPS runtime scheduler at 0 to boot up. Actually, everything stuck on some places, but without any log. So far, I didn't debug more. So we just clear performance first.